Welcome back to another lecture on threads part 2. We are going to look at the following topics under this part 2, and we are not going to do coding at this moment. We will do coding because there's a lot of things to cover. So if we do coding for each one of these, we are going to have a very long video, a very long lecture. So we are trying to put things separately. So we are just going to look at this in theory. So what is an executor? An executor is an object that executes submitted runnable tasks. This interface provides a way of decoupling task submission from the mechanics of how each task will be run, including details of thread use, scheduling, etc. So an executor is normally used instead of explicitly creating threads. For instance, rather than having to invoke new thread and give it a task and start it for each set of a task, you might need to say executor equals to my executor. Then you are done. You can always pass your executor a task to execute it. Then this is the hierarchy of the executor interface and all its subclasses. So we see that ExecutorService extends executor. Then we see that ScheduledExecutorService extends ExecutorService. Then we see that the ExecutorService also has abstract ExecutorService. We see that abstract ExecutorService extends, or you can say it derives from ExecutorService. And below abstract ExecutorService, we see we have ThreadPool Executor, ForkJoin pool, which directly derive from it. So what is an ExecutorService? It is an executor that provides methods for managing termination of tasks, methods that can produce future for tracking progress of one or more asynchronous tasks. So an executor can be shut down, which will cause it to reject new tasks. So two different methods are provided for shutting down an executor service. We have shutdown method, which will allow previously submitted tasks to execute before terminating, while the shutdown method prevents waiting tasks from starting and attempts to stop currently executing tasks. Upon termination, an executor has no tasks actively executing, no tasks awaiting execution, and no new tasks can be submitted. So an unused executor should be shut down to allow reclamation of its resources, because they are resource intensive. So here you see the implementations of the executor service, or the classes that derive from it. Then we have a scheduled executor service. This is an executor service that can schedule commands to run after a given delay or execute maybe periodically. The scheduled methods create tasks with various delays and return a task object that can be used to cancel or check execution. Then we have the schedule at fixed rate and schedule with fixed delay methods, which create and execute tasks that can run periodically until cancelled. Then we have executors. So executors is a utility class which will allow you to create executor service, scheduled executor service, callables, thread factory, and all that. So we see that methods that create and return an executor service set up with commonly used configuration settings. This is what you can get from executors. It can also create a scheduled executor service, as we saw. Then executors Inside executors, we have a couple of methods that are used to give us back executor. We see we have new thread, new fixed thread pool, we have new work stealing pool, and we also have new single thread scheduled executor. And you find that this method, some of them are overloaded. So if we can go into the code just to look at the executors, as you can see, we have new fixed thread pool. It's explained what it does. I recommend you to read about that, but some of this we are going to look at them when we are doing the demonstration. We see new work still in thread pool, and you see it's overloaded. We see new fixed thread pool, and you see that we had it before new fixed thread pool, it's overloaded. We have new single thread executor, new cached thread pool, it's also overloaded, and many others like new single thread scheduled executor, as I mentioned. So we have again what we call synchronizers. So a synchronizer is a high-level abstraction for synchronizing activities of two or more threads. So we have a CyclicBarrier, which actually provides an execution point where each thread needs to wait until all other threads reach that particular point. So if all the other threads have not reached that point, a thread will not be able to pass that particular point. It will only pass if all other threads have arrived. Then we have a CountDownLatch, which allows one or more threads to wait for a countdown to complete. So until a countdown has completed, threads cannot be able to proceed and do what they need to do. Then we have an exchanger, which is used for exchanging data between threads. Then we have what we call a phaser, which is useful when few independent tasks have to work in phases to complete a task. Then we have a semaphore, which controls access to shared resources and maintains a counter to specify a number of resources that the semaphore controls. So in our demonstration, we are going to only look at only two synchronizers, the CyclicBarrier, the CountDownLatch, and if I have time, I will work on the phaser as well. Then atomics. So we see that when you are working with primitives and you want to have, you have a primitive type, and then you have many threads operating on it. You always need to do acquiring and releasing of logs to get synchronicity, so that at the end of the day you have reliable data. So Java has actually created an efficient alternative in the form of atomic variable, so that you don't need to be acquiring and releasing logs when you are performing arithmetic operations on the primitive types. Then the AtomicInteger, we have the method get and set, get and increment, get and decrement. So we'll look at all these, some of these methods when we are doing the demonstration. Then we have parallel streams. So parallel streams, what it does, it's actually under the streams API. It will split data into chunks and process each chunk with a different thread, and if necessary, combine the results. This reduces time to process significantly. Imagine you have a very large data set and you are working on it on one thread. You will have to wait. But if you break down that data and give each chunk to different thread, you're going to have just a short time to work on that particular data. So you can think of it as something like divide and conquer. So parallel streams internally use ForkJoin pool, and the process should consist of stateless and independent tasks for the parallel streams to work. Your data must be stateless and it must be independent. You must not have stateful data. So we see here that this is just an example that we will see when we are doing the demonstration. That we have primitive stream and we are filtering numbers between 2 to 100,000. We filter, we only want to get we want to count how many prime numbers are there. Without parallel streams, we find that we have like 2 to 3 seconds. We can even have more than that. But when we add parallel, it means we are asking the runtime to give us an implementation that is parallel, that will allow us now to divide these numbers here into chunks and be assigning them to different threads to be checking for us if they are prime. And then when the threads are all done, we combine the results, then we return them back. So in this code, the work is computed. The work to be computed is split. Then when to use parallel streams? You use parallel streams when you are dealing with significantly large data sets and we are dealing with computationally expensive operations and the data structures are efficiently splittable. That means they are independent and they are stateless. Then we have concurrent collections. So concurrent collections provide a number of collection classes that are thread safe. Mostly our collections, the ArrayList, the hashmap, the other kinds, or maybe the hashmap, you find that they are not thread safe. The hashmap and the ArrayList, they are not thread safe. Now, for you to have thread safety, you have to now use concurrent collection. The concurrent hashmap is thread safe. Then you have the blocking queue. It's also thread safe. Then under blocking queue, we have a number of implementations: ArrayBlockingQueue, linked, delay, priority blocking queue, and synchronous queue. So we are only going to work on the ArrayBlockingQueue. I highly suggest that you actually create code to explore and play around with the other implementations. Then we have another concurrent collection. It's called CopyOnWriteArrayList. So ArrayList is not thread safe, but CopyOnWriteArrayList is thread safe. Methods such as remove, add for an ArrayList throws a concurrent modification exception if another thread modifies the ArrayList while another thread is busy accessing and iterating the ArrayList. However, we have methods in the CopyOnWriteArrayList as well as CopyOnWriteArraySet. They do not throw that exception. Why? Because the iterators of those classes, they access originally a modified collection. So it's like you have two sets of data here. So now, if that is the case, it means when you are looking for performance, you might not want to work on these two because they will delay you. Then we have a ForkJoin. So ForkJoin, by default, ForkJoin ThreadPool has a number of threads equal to the number of processors available to the JVM. So when you create a ForkJoin pool, it gives you the number of processors available into the JVM. And you can also be able to get that number by saying runtime.get runtime.available processors. So this ForkJoin pool, as I said, is internally used by the parallel streams to divide work.